seconds or so. I think, yeah, live. Cool. All right. Let me just refresh this page. And screen's okay. Hasn't started yet on YouTube. That's okay. All right.
A delay, doesn't it?
Let me reload that. Live.
Nathaniel likes your ASCII graphics.
Yeah. I quickly put that together. Okay. This is being really slow. Okay.
Not working?
No, it's working. I just want to get something up, and it's not opening. I see. Okay, cool. So that's that. That's that. Right. Sorry about that, everyone. All right, let's start. Okay, so in this help session, we're going to go through some of the content that you need to know for next week, as well as retouch on some of the content you've already done, just that we found some of the students struggled with. So to start with, what I want to quickly do first is just retouch on typecasting. So in the labs, and you've been doing different equations where you've had two ints, let's say. This isn't a very good pen. You've had two ints, say A, B, and then you've had something like float C equals A over B. Now, when these are given values, they have to be whole numbers. So let's say we initialize A to 1 and B to 2. So with this, the order of operations is A over B, and then it gets stored into C. So when A and B is computed, you've got you've got an int divided by an int, which is an int. So in this case, we've got 1 divided by 2, which normally would be 0.5 in pure mathematics, but because we've got a limited storage space and we're specifying a type, it's actually 0. So don't forget this. Every time you have an int over an int, we end up with this problem. So how we get around this is we typecast. So get rid of that, and instead we would write something like this: float C equals float A over B. And what this does in terms of order of operations, this happens first. So this cast happens first, then the division, then it gets stored into C. So this time what we see is when it's computed, we have float 1 divided by 2. Then this gets computed first, so 1 gets turned into a float, so we get 1.0 divided by 2. And because we've got a float over an int, we get a floating point answer. So we get the correct answer. So this one here, we would have got 0. This one here, we would have got 1.5. So whenever you've got two int variables and you have a division, be careful. The same applies for plus, times, and subtraction, but we don't end up with a like decimal places caused by adding two numbers, two ints. It's only when we divide two ints that we get decimal places introduced. Is there anything you want to add to that, Josh?
I think you've pretty much covered the main bits. So yeah.
Yes. Cute. And one other thing is that you can cast to any type. So if you want to cast to an int, it's the same thing. You just put int in the brackets. If you want to cast to a character, you put character in the brackets. If you want to cast to a double, you put double in the brackets. So you can change the type during an operation if you need in any expression. All right, what was the second thing I had? So next thing, just quickly, the printf statement. So, oops, printf is a function. Now, functions can have a number of arguments, and this is where the arguments go. It can also have return values, which you'll do in later weeks, but we won't worry about them too much. It also has a name. Okay, so this week you would have seen, what functions did you do? I think you, let me have a look. Okay, so for example, I think you did the power function. That had arguments. So arguments are separated by basically this comma here. So this is the first argument, this is the second argument. Now, there's some functions that can have as many arguments as they need, and printf is one of them. However, the first argument is always just the text. So this is always the text. And then the arguments that follow are numbers that you want to put into the text. The number of format specifiers is the number of arguments you have here. So really, you can know if you've got enough arguments by counting how many percent symbols you have in your printf. So if you've got 2% Ds here, then you should have 2 arguments. So let's say the letter A and B. If you add another %D, you need another argument. You cannot do anything but show text in the text. You can't perform calculations. So the text is purely text. So if you do A plus B, all it will print is A plus B. If you do %D plus %D, and you give it, let's say, the number 2 and the number 4, then it'll print 2 plus 4. It's not going to do anything more than that. Was there any other things that people were doing strange with printf?
That was the main thing, just when you're printing out stuff, everything you put in that string will just print out as a string. So like what you said with the a minus b, a plus b.
There's no calculations here. However, you can do calculations in the argument. So if you do 2 plus 1 here, it will evaluate this and then put it here. So in this case, if we had 2 plus 1 as one of our arguments, then we'd get 3 plus 4. Yeah? Anything
Cool.
else?
No, I think that's pretty much it. It's the main things, yeah, just to be careful with that. So.
Okay, what else do I have? So, the next one, just a big reminder, with the scanf function, if you use %f, let's say, when you did printf, you may have done something like point to f. Now, when you're doing scanf, oops, that's a horrible address. When you're doing scanf, you don't include these options because the user can put in whatever they like, and you will get a warning. The other thing is, you'll get to this in week 5 or 6. Whenever you're using scanf, you need the and symbol before your variable. This is basically saying that we're looking at the address, and you'll get to why we're doing this in later labs. The other thing is that you can put more than 1 or 2, and we'll go through a quiz question later that had this thing, but you can put 2 Ds here, let's say, and then have so A, B, and then if you enter 2 numbers, let's say there's a space here, the first number will go into A, the second number will go into B. And we'll go through some more complex cases right now with the scanf, because we're talking about it. So I'll grab the quiz questions up that relate to scanf, all right? So that's conditional. So we have, yeah, this one. Josh, do you want to go through this?
Yeah, sure thing.
Do you want the screen, or do you want?
Awesome. Oh, your screen's fine. Can you make it a bit bigger, little though? Maybe? Maybe it won't do much. Yeah, that's right. So this was a question that did trick a few people on the quiz. So given that the user input is as follows, so negative 20.3, 54.4, which call to scanf will execute correctly? So this question's probably trickier than it sees just by looking at it. When we look at it, we can see that we've pretty much got 2 floats there because we've got 2 decimal numbers separated by a comma. So when we're scanning in, because the comma's there in the input, we actually have to take that into account when we're scanning in for the user input. So when we first look at this problem, we might think that C could be the answer because we're scanning in 2 float variables. However, we have to be careful with that comma that's in there because this actually means that C won't work because we have this comma there. Following from that, the next thing we probably think of is A because there is a comma inside here. But next thing we have to be really careful of is we don't have the ampersand in front of our variables at the end there. So every time we're scanning in something, we need to make sure that we have the ampersand in front of our variables at the end. If the ampersands were there, A would work. All right, so by that logic as well, we've just gone through, we can cross off B straight away because there's no ampersands for our variables. So we're left with D and E as our answers. And we can see the only difference between these two is we have commas after the percentage D, percentage F, percentage D, percentage F. And we have commas just in the middle for D. And I think there's also a typo in there. I've forgotten to close the thing, but no one's picked that up. Awesome. So what we're looking for is we're seeing that we're trying to scan in integers, which is probably not what we think when we first look at this problem. But just looking, it's gone away.
Yes,
Thank you. When we look at the input, we can actually see that we can. It's gone again. It's all right. We can make this up of integers if we read it across. So the first integer that we see is -20 before that decimal place. So if we try to scan in an integer, the first thing we'd scan in is that -20. And then the float that we scan in would actually be that 0.3 or the 0.3 that's left. And the same thing happens on the other side of that as well. So when we try and read the integer, we'd scan in the 54. And we try and read in the float, we scan in the 0.4 that's left over. So this was a tricky question because that's pretty tricky to see, especially looking at you think that it is probably just two floats straight away. And in this case as well, as we were saying before with the comma, we've got the comma in the middle of the two numbers. So we've got to have that in our scanf just so we can pretty much get rid of it from our input. So that's why we should get D there as our answer. Did you want to add anything else to that, Matt?
There's a typo.
There's a typo. Yep. No one picked me up on it though, so that's all right.
It's still wrong anyway.
Exactly. Maybe that was the reason. Yeah.
No, that's good. Yeah, what's the question? So that's that one. Get rid of that. Is there any other scan? Oh, this is the other scanner one. So I'll open that one up.
Cool.
And while you do that, I'm going to chuck the link on. I'm going to put an announcement on LMS.
Sure thing.
Find LMS. Sorry. There we go.
That's all right.
You got the question there?
Yeah, it's on your screen. Yeah. Cool. All right, so we've got another tricky question here. So this one pulled up a few people as well. So given that the user input is as follows, 17, 2.75, what is the output of the following C program? So looking at this from the top to the bottom, because our C code is sequential, first off we see we've got a few variable declarations. So we've got an integer A, an integer B, and a float C. All right, now when we're scanning in our numbers here, the first thing we're scanning in is an integer. So we can see straight away that it'd pick up 17. Then we've got this comma happening again. So again, what this comma does is it just says that when we're reading in the user input, we can just ignore the comma that's in the user input. Next thing, we're reading in another integer. So what we're going to be doing is, same as last question, we're only going to be reading the number 2 into that variable, not anything else, just the 2. And then finally, when we're reading the float, that'll just be our 0.75. So again, this is something to definitely watch out for because it can be a bit tricky to sort of think that the float takes in 2.75 or something like that. All right, so on the next line, we've got A is equal to 17, and we're saying that A is A mod 10 plus B. So looking at that to start with, A mod 10, with the modulus operator, for those that don't know, this just says after the division, we're looking for the remainder. So when we divide 17 by 10, that's going to be 1 with a remainder of 7. So when we use that mod... What's that?
Give a couple of example, 17 mod 10.
Yep. So when we do 17 mod 10, we can see that that's 1 with a remainder of 7. So what happens when Matt draws it on the screen? Awesome. So we just grab the remainder, and that's the part that we keep. So same thing if we do 27 mod 10. The answer is still going to be 7 because we're only keeping the remainder of the division. So this is, you might have seen this before, you might not have, but it's something just to watch out for when you see the modulus operator. All right, so we've gone 17 mod 10, and that's given us an answer of 7, and then we're adding b. So again, b was equal to 2 at this stage because it wasn't anything past that 2. So right now, a should have a value of 9. All right, then on the next line, we're saying c multiply equals b. So when we see this multiply equals, it's actually a shorthand notation to say c equals c multiplied by b. We can do this with plus equals, minus equals, or divide equals. But all we're saying is c equals c times b. So we saw at the start that c was equal to 0.75. We know that c is a float as well, so we might have to remember that just in case that might come back. So we're saying c is equal to 0.75 times 2. So that should give us a value of 1.5, if my maths is correct. So right now, we've got a equals 9 and c equals 1.5. And then we're hitting our print statement. So we're going to print out result, percentage 4d, percentage dot 2f, and we're printing out a and c. So if we start with c, just because we just calculated it, we know that we need to print c to 2 decimal places, and c had a value of 1.5. So we should be printing 1.50. So straight away we can cross off the top result. Next thing, we saw that our a value was 9. So right away we can cross off c and e. So now we're only left with b and d. So the only differences here is that one of them is aligned to the left and one of them is aligned to the right. So again, we've covered this last week. When we have the percentage 4, this tells it to how much to pad it to either direction. So it says that we should reserve 4 spots to print out this number. Because it's percentage 4d and it's not percentage negative 4d, that means that we need to format it and put it to the right-hand side of those 4 spaces. So we should find d is our answer here. If it was minus 4d, then that would mean we align it to the left, and that would mean that b would be our answer.
Cool.
Awesome.
Alright, so that was that one? Yep. Cool. Alright, I just sent out the link.
Awesome.
Sorry.
Hopefully someone sees it.
Oh, here we go. This way.
All right, so is that we're going through that one now?
Someone's saying they can't join because they don't have a Google account.
Should be able to look at the YouTube link still.
Yeah. I'm watching the second half session live stream, but unfortunately they can't join. Oh, they can't join the thing.
The Hangout.
So if you're not able to join the Hangout, you can write your questions. There's a chat in the YouTube. So on YouTube, if you go to YouTube, there's a chat here that you can type stuff if you want to ask any questions. All right. Well, that's a good one as well to cover right now.
Cool.
Do that one.
Yep.
Let's get rid of. Sorry. There we go. Get rid of that. There we go.
Cool. So what is the output of the following? So we'll just go through the code from the top to the bottom again. We've got int x equals 16, so we've got a variable declaration and we're initializing it with a value of 16. Then we've got an if, so if x equals 8, print x equals 8, and then print out end at the end. So straight away, just by looking at this kind of seems like a bit of a silly question. I mean, we can straight away see that 16 doesn't equal 8, so we should just print out end. But in this case, it's actually a little bit trickier than that. The trick comes up in the if statement. So having a look at it, if x equals 8, now something we really have to watch out for is we've only used a singular equal sign here. Normally, or all the time, if we ever want to compare two values, we need to use a double equal sign. When we use a single equal sign, we say that it means becomes, or we assign a value that way. So like at the start, we said x equals 16. We used a single equal sign because we wanted x to have the value of 16. So when we've said in the if statement, if x equals 8, what we've actually done is we've given x a value of 8, and then C interprets this as the condition's true, so it goes inside the if statement. And this is something that tricks up a lot of people, so it's something you really need to watch out for, the difference between a single equal sign and a double equal sign.
Just wait.
So, yeah?
Oh, sorry. Keep going.
Yeah, all right. So because of this, the condition in the if statement is true, so we're going to print out x equals 8, followed by a new line. And then, of course, after we get out of the if statement, we're still going to hit that last printf. So we should be printing out x equals 8, then on a line underneath that, we'll print out end. Did you want to add something to that, Matt?
Yeah. This cutter.
This cutting, yeah. So, yeah, this is a pretty good reason as to why you should never forget the double equals. Otherwise, everybody dies.
So the joke here is basically they're saying that they programmed the robots not to kill them. However, as you can see here, they haven't got two equals. So is crazy murdering robot becomes true. And so this will be true, and so it'll do this statement, rather than be nice to humans.
Nobody has a good time.
Nobody does. And that's why you should do it, because if you're programming robots and you have that statement, bad things can happen. Alright, so that one's done. Alright, so that was that one?
Yep.
Yep. We'll come to if statements. That one's ternary. That one's case. And that one is ternary. Do you want to take over the screen and explain the ternary operator?
Yep. Do you want to bring up which question have you got there so I can...
Oh, just a general overview and then... Oh, yeah, you want the question?
Yeah, which question? Just so I have an example to go off would be nice.
That one?
That one? Cool. What's that? What's it called? W3C4.
I'm going to shut the screen over to you.
Cool. Alright, it's on my screen, so this is the one here. Cool. Alright, so something new we might have seen on the quizzes for week 3 was this ternary operator that we've got on the screen here, so this question mark. When we use this, we can sort of think about this whole thing as an if statement. It's just a bit of a shorthand if statement. So as an example of this, let me just... Cool. So over here, we're saying A equals A less than 0, question mark. And then we've got some more stuff here. We've got a colon and we've got negative A and positive A. So just before we get to this statement, drag this down. At the top of here, we've said that A is equal to -5. So the first thing we do when we see these ternary operators is we look to the bit just to the left of the ternary operator. So the bit to the left will always be some sort of condition that can either be true or false. So looking at this, A is equal to -5, and then we're asking, is A less than 0? So it kind of makes sense. A less than 0 question mark. Is A less than 0? And in this case it is. So what we see is after we've got that question mark, we've got two things separated by a colon. So we've got -A, colon A. Now what happens is, depending if this is true or false, one of these things is returned. And I'll go through that in a moment. So we saw that this was true because -5 is less than 0. So what happens is we grab the first thing, so the thing to the left of the colon, and we return this because this is the true condition. The one to the right of that is the false condition. And that'll make more sense in a moment. So what we're doing is we check the condition. We said this is true, so we're going to grab this -A. And what the statement then effectively becomes is us saying A equals -A. So instead of saying something like if A is less than 0, A equals -A, else, you can see this is going horribly, A equals A. So you can see that doing this in one line is actually the same as doing this big if-else statement. So sometimes we use this just because it does look a bit nicer, and if we understand it as well, then it is pretty nice to use. So going through that again, first off, we're saying, is A less than 0? If A less than 0. We found out that A was less than 0, so we go to the first bit after the question mark, which is as if we were just entering this part of the if statement. If it wasn't true, if this was false, what we'd be doing is we'd be essentially going to the else, if we can kind of think of this as an if-else statement. And if we did that, we'd pick up this A. Then once we do that, all we're saying is A is equal to whichever one of these that we chose. So in this case, we found that A was equal to -A. If we go back to the quiz question again, over here, A is equal to, is A less than 0? It is. So A is equal to -A. So if I, over here, we're going to find, after that first line, A is equal to 5, because -5 is just +5. On the next line, is B less than 0? B is not less than 0. So this means we're going to be choosing the second bit, so the bit after the colon in this case. So what we're just saying is B is equal to B. So B just stays the same as 2. Then we're saying int C is equal to A less than B, so is 5 less than 2? 5 isn't less than 2, so we're going to be choosing that second bit again. And so what we're saying is C equals B. And in this case, C just equals 2. And that's how we deal when we see these question marks, these ternary operators. So they're pretty cool. They cut down a fair bit of code. So from before we had about 5 lines of terribly drawn code. So we could have that, or we could just have 1 line of code, which is quite nice.
So Josh, you just got a question.
Yep.
In the chat. Might need to re-clarify a little bit.
Is colon the same as double equals? Cool. So in this case here, the colon is sort of special with this ternary operator when we use it. So we're actually doing an assignment. We're not comparing values, we're doing an assignment. And what I mean by that is when we say A equals, this is the part here. This is where the assignment happens. All the bit to the right of that does, so when we have a less than 0, question mark, negative a, colon a, all this is doing is we're just saying if a is less than 0, we're going to return this value here. Otherwise, we're going to return this value here. And when I say return, all that means is if a is less than 0, we're going to grab this value and place it here. Otherwise, if it's not less than 0, we're going to grab this value and place it here. And then we've just got this assignment. So again, we're only using the single equals. When we use a single equals, we're saying that A becomes whichever one of these two. So when we see this colon, just to recap, this colon is just a way that we can separate these two outcomes. And we use this colon when we have the question mark or when we're using this ternary operator. Does that answer your question? You'll have to help me out with that, Matt.
Yeah, I just sent a message.
Cool. Do you want to add anything to that explanation as well?
Don't forget semicolons.
Of course, yeah. Semicolons are really important. I just thought I wouldn't put you all through the terrible paint skills that I have. But yeah, semicolon at the very end of that line. So that's just like normal. To end our lines in our code, we always use a semicolon.
So this is some stuff I got.
So minus a would be 5. Yeah, exactly. So we saw that at the start, a was, 1 second. There we go. So we saw that at the start, a was just equal to negative 5. Then what we said was a is equal to negative a. We found it was negative a from this operation that we went through here. Then all we're doing here is, at the start, a was equal to negative 5. So we grab this negative 5, and we do this. So we just replace it where we see a, and then as we know just in normal maths, if we see two negative signs right after the after, it just becomes a positive. So yeah, exactly. A becomes 5.
Beautiful.
Negative and a negative makes
So what
positive.
I might do quickly, one thing I want to do is quickly show how if statements evaluate.
Sure.
So I might jump back on the screen, unless there's anything you want to add, and then we'll go to binary stuff.
Yeah, unless anyone else has any questions at all. Hopefully that answers your questions. But if you do, definitely leave a message and we'll explain it in a bit more detail.
So if anyone doesn't know, there's a chat both on the Hangout and the YouTube, and I'm watching both of them. All right, I'm going to take over for a little bit. Okay, so the next thing is that we saw this week was the if statement. Now, I think most people understood the if statement pretty well. The thing that I saw a couple of people got stuck with was the stuff in here. So this is the condition, and this gets evaluated. Now, it's really important. This is still a number, and basically the if statement works. Anything that is not 0 is true. So, and anything that is 0 is false. So 0 is false, and 1 is true, and anything else is true. So just a quick example, if I put if 0 here, then it will always go to the else case. If I put if 1 here, it will always do this case. Now, why this is important is because what I saw a couple of people doing was A less than H. Now let's give it a value. 4. Let's say 4 less than H, and then we got 9. Okay, so if we have int H equals, let's say, 0. Yeah, 0.
0 is good.
0 is good. What will happen is this will happen first, then this. Remember, all of these are binary operations between two. The only special case is the ternary operator, which Josh went through earlier. So this happens, and then the result of that is compared to here. Now, with any conditional, it returns a number. So 4 is less than 0. Is that true or false? I got no response.
It's true, it's true.
So 4 less than 0 is false. So it actually returns a 0. So that means that we've now got, so let me write it out. So we've got 4 less than 0, 9, and this evaluates down to 0 because it's false. Is 0 less than 9? Yes, it's true.
No.
So it's a 1, meaning this if statement is true. So anytime you're trying to compare two things, or 3 things, or 4 things, or ever many things, so H, I can't remember what example I had. I think it was 4, wasn't it?
Yeah, 4 and 9.
You need to specify either and, something like that, and or. Now, and will say if both of these are true, then do this. This will say if one of these are true, then do this. Now, with this, the same thing happens. So 4 is less than, what will happen? 4, 0, which is false. So this becomes 0. Now, a special thing with C and a lot of programming languages, because there's the and here, even if this is true or false, it's always going to be false because one of them is already 0. So it won't actually evaluate this because it's pointless. Just something to keep in mind. We will deal with that later. And if it was or, then it would check both. So the if statements, just remember that you're still dealing with numbers and binary operations. Now, while I'm talking about binary, now when I say binary operations, I mean between two. Okay? Now, while we're on that, let me see if there's any questions around that. Yes, there was. All right. So, let's have a look at this question. So here, we've also got another symbol, which is not. Yeah. All right. So let's go through this question. Where are we? I want to move this around. Put that down. Okay. So, we've now got this question here, which has int result equals 1, A equals 3, B equals 5, C equals 3. So let's draw these out. So we've got, now let's do it this way. We've got a couple of ints. We've got 4 ints. The first one's called, I should have made this so small, result. The second one is called A. Third one is B. And the fourth one is C. And we initialize these to 1, 3, 5, and 3. That says result. Okay, so we've got our values. They're all ints. B, C. Then we get to this if statement. Dun, dun, A less than B. Oh, run out of room. Equals takes precedence over 4, yeah?
Yep.
What takes precedence for a not? Logical not?
The not comes before the
Cool. Just want
and
to double check
yeah.
that.
Sure.
Okay. So we've got this big ugly mess. Now, one thing I will also add, it's good to put brackets around these, just so that it looks nice. Okay, so in terms of order of operations, you can see this, look at the red. This one happens first, then this one, then this one, then this one, then this one. So, who's knocking? What are you doing, Josh?
Nothing.
Let's write this out.
Someone's up
So
there.
A equals 3, less than B, which is 5, or C, which is 3. Oh, so someone just asked what the double dash means. It means or. So if this is true, or this is true. Now I've drawn brackets around there just because out of sanity. There's another bracket there. So we'll see what that does in a second. Oh, didn't mean to write result. All right. Now, just give me a sec. Okay, so we've got this here now. So this one happens first. 3 is less than 5 is true. So we get a 1. Or 3 is equal to 5, which is a 0. Now, as the question that just got asked, what does this do? It does or. So if this one's a 1 and this one's a 0, or this one's true and this one's false, then it becomes true. If they were both zeros, then it'd be false. If they were both 1s, it'd be true. The AND, however, compares two different things and want them both to be true. Now, this symbol here, the exclamation mark, is a logical not. So this is a 1, and 1 is a truth value. So this will actually become 0. And this is a 1. And so we get a 0 because true and false, they both have to be true. Did I miss anything?
No, I think you've got it all.
Cool. Okay. So the if statement fails. And so the result should be 1. Yeah?
That's of the if. You didn't do the result bit.
It doesn't do it because it's 0.
Oh, sorry. Wait, I can't even see the screen. All right, never mind. Yeah.
Yeah, so it doesn't do this part because this fails. However, let's have a look at this statement anyway because it's nice and interesting. So the answer is 1 because result doesn't change. We never change result. But let's have a look at this statement in the middle. Does that make... Why does not 1 become 0? Okay. So... 0 equals false. True. 1 equals true. Everything else equals true. So this is the returned false value, and this is the returned truth value. So if I do a logical AND between two things and it was wrong, then it returned 0. If it was true, it would return a 1. So when we see not result, result is a value, and its value is 1. So logically, 1 is true, and this symbol will turn it into false. So it becomes 0. Now it's false. The same would apply if result was 5, 6, 10, because anything else is true. So not 5 is also 0. It's a logic operator, so it's looking at falses and trues, and you should try and not use it for maths. Does that make sense, person in the chat? Reload that.
The chat's delayed, isn't it?
Huh?
The YouTube video is delayed.
It is too.
Yep.
Yep.
It said yep.
Cool. Yeah, there's a 30-second delay.
Something like that, yeah.
I'm pretty sure. I set it so that I didn't kill my computer. Okay.
So what does result equals A exclamation equals C mean?
Okay, so now we've got this ugly statement, which is result A not equal to C, and we've got C, oops, is 3, and we've got A is 1. So just as before, this will evaluate first, and then it gets stored in result. Now, A is not equal to C. We've got 1 is not equal to 3. For a truth value, this is false. This is true, actually. This is true, and so you get a 1. So either way, you would have got the right answer.
that was unplanned.
I'm just having a look here. I think this question is the same. Cool, it is the same. It's very similar.
Pretty similar, yeah.
Okay. Do you want to quickly go over a case for this question, and then
Sure.
I will take over. So I'll chuck it on your screen.
Alrighty.
A sec. Present to everyone. Yep, you're presenting.
I also brought up this orders of precedence, but I don't know how important it is to go through.
Oh, you can if you want quickly.
Yeah. All right. So just to add to what Matt was saying, this is why brackets are really important, because C has an order of operations. So depending on what you're trying to do, so if you're trying to compare things if they're equal with the double equals, or if you're trying to do the logical not,
It's like
depending on.
I'm sorry. It's
Yeah,
like an extended bot math.
Exactly. So always brackets come first. So this is why bracketing your statements is really important, because sometimes, doing a logical not has higher precedence than doing a logical and. So if you wanted to work out something, maybe you were trying to do 5, not maybe 3
I don't know.
and
Sure.
5. I don't know if that works, but anyway, essentially the not comes first.
I don't think you're up on the screen. Oh, no, you are.
I
don't
am.
know what happened. Yeah, okay.
Cool. Is that all good now?
Yeah, it just wasn't showing you up.
Okay, that's strange. Yeah, so essentially if you were trying to work out something like maybe 1, not, and not 0 or something. So it'll always do this not bit first before it does the and. And in some cases, this can actually change the result. Normally it's okay, but essentially just always make sure you're using brackets. That's the main thing. All right, so on to the case statement. Let me just bring that up. Do you know what question that was?
W3C2.
C2. Alright, so what is the output of the following? Int game equals 1. And then we've got this switch thing happening here. So what a switch essentially does is, depending on a variable, we have a few different cases. So essentially a switch is kind of another way we can do a really big if, else. So what we might be saying here is, if game equals 0, do this. Else if game equals 1, do this. Else if game equals 2, do this. Switches are a bit different though, so we'll go through this one in detail from the top. So what we do first, we've got switch game. So at this moment, game is equal to 1. So what we're doing is we're looking for a case where the case is 1. So having a look, we go through case 0. 0 isn't 1, so we ignore that. Case 1, 1 is the same as 1. So we hit this case, and what we do when we hit the case is we actually execute what's inside it. So the first thing we'll be doing here is we'll be printing out cricket. Followed by a new line as well. So we're going to jump down to the new line here. Now, this is where switch statements are different to if-else's and all the rest of it. What actually happens is, if we don't see a break statement, so a break statement is essentially where we just actually have the word break followed by a semicolon. What this does is it tells C to exit out of this switch statement. What happens if we don't include this break statement, which is what's happening here, is we just keep on going through sequentially. So we found that we're after case 1, we've executed this line of code, we're going to ignore that this is here because we don't see a break statement. And what that means is we're going to execute the next line of code that we see, which is printing football. So the next thing that happens, we've entered in case 1, we printed out cricket, we didn't see a break statement, so we've gone to the next statement that we see. We're printing out football, followed by a new line. This was the tricky bit of this question. So normally switch statements are pretty straightforward. Normally we have a break in there which stops us from falling into this trap. What happened next is after we printed this out, there's nothing left in our switch statement because there's no more breaks here. So if there were more statements, we'd execute those. We exit out of our switch statement because we've hit the end, and then we print out end of list. So in this case, we find cricket, football, end of list. So we find that A should be our answer. And again, this is something to be really careful of. If you don't see a break statement, the code is going to keep on executing inside of that switch. So just the next statement it sees, it's going to execute. Did you want to add anything else to that, Matt?
So just in terms of good practice, just include break after everything for now. Unless you want to do something tricky and special, it's just good practice to put break after every single case.
Definitely. Yeah, because if you don't include it, it can give you some weird results that you don't expect if you don't know why. So definitely watch out for that one.
All right.
What other ones did we have? What was that? What were you going to say?
If you go to the statistics, you can see the difficult ones, but I think they were the main ones. What I want, no, I've got a couple more from the previous week, but what I wanted to go through was I'm going to quickly show binary hex.
Are you going to do that one?
I haven't got a question for it, but I'll quickly go through it and then you can show how to do it on a calculator and all that.
All right, cool.
Okay.
Sounds good.
All right, so I'm going to take over the screen. Nice background.
Thanks. It's been on there for a year or two now.
This. All right. So some of you may be aware, some of you may not, but when we're talking about an int in the Unix environment, we're talking about 8 bytes of data. So, well, 4 bytes, sorry.
8 bytes, that's pretty big.
We're talking about 4 bytes of data, and each of, basically a byte equals 8 bits. So each one of these is 8. So 8 here, 8 here, 8 here, 8 here. 4 bytes. So altogether, 8, 16, 24, 32. So this is 32 bits. Now when I say bits, basically a bit has 2 conditions. It can either be on or off, or what you can think of as on or off, or 1 or 0. So you can think of it like a light switch. It can be either in the on state or the off state. 1 or 0 state. And an int, to represent a number, has 32 of these. Now, a short int, so short, is 2 bytes, and so it will have 16. Now, some systems will be different because int is system dependent, so you may find some systems have 2-byte ints. So make sure you always check, especially if you're going to do something like embedded computing or work on a different system in the future, or working on an old system or a very new system. Okay, so we've got that. Now, how do we represent numbers if we've only got on and off switches? So we've got a bunch of on-off switches. We're just going to look at 8 for now. So this could be a car, because a car only has 8 bits. So
When you say car, you mean character, just to clarify?
yeah, well,
Yep.
it's a car. It's a car.
Like a Toyota or a Mercedes or something?
Yeah. So
Cool.
car is just a number. It's specifically designed to hold characters, but it can hold numbers because the ASCII code is actually just numbers anyway. So when I do something like car, well, actually I'll do it as an int, so that makes a bit more sense. So if I do int a equals 4, what happens in memory is we get the that happened before. That's not the one. Sorry. Delete all that. What happens in memory is basically we have all these zeros now, and one of these get set to a 1. And the reason is because this is the number in binary representation, and this is how it's stored. So all your numbers, whatever you enter, will be stored as a binary number. So another example, if I said a equals 56, then we get, I'm really going to make the eraser smaller.
Mm.
If we have 56, then we get an 8, 16, 32. We get this in memory. And this is its binary representation. Now, what I can also do, because of this, I can specify the number in different formats. So if I did this and wrote 0b, specifying that I'm writing the number not as a decimal, but as a binary number, I can't see the YouTube chat, by the way. Yeah.
I'll keep an eye on that if you want.
Yep. If I write this instead and do something like printf, sorry, keep zooming. If I do printf %d a, what will it print? It will actually print 56 because this binary number is 56 in decimal. Now, another useful number system that we use in in programming is hexadecimal. So hexadecimal looks like this. So 0x, and for us here, the number will be 3. Oh, what happened there? Why did it come all big? It will be 3, 8. Okay, and same thing. The number is in hex, but it'll still print out as 56 because we're printing out a decimal integer. If, however, I did something like this and change this back to 56, and I change this to an x, which is hex, it will print out 3, 8. Now, there's no format specifier for binary, but there will be a bonus question, I think, next week to do that, to print out the binary representation. So keep a lookout for that. But this is why, and the other thing we can do, so if I get up the ASCII table and find out what 56 is. So if I get the ASCII table up and I look up 56, 56 is the character 8 in decimal. So if now you will get warnings, most likely. But if I put a C here, it will print the character 8 to the screen.
We've just got a question as well on the chat.
Which chat?
I'll just post it to this one.
How do you determine which binary combination gives a certain number? Okay, so there's a calculation for that, but Josh is going to show you an easier way for now, at just using a calculator. Basically how it works is this is 1s, this is 2s, this is 4s, this is 8s, this is 16s, this is 32s, 64s, 128s, and so on. And so 32 plus 16 plus 8 equals 56. And that's how we get the number. But Josh will show you a way to convert between them. So I'll get him to do that. Was there anything else about binary?
I think that's basically.
Can
say that. Hey.
You go through conversions. We'll do bit bashing a little later.
Yeah, we can do that later in the thing. Yep, that's cool.
That's cool. Right. I'm gonna pass it to you to show how to do the calculations. Give it a sec. I just want it to go to you. Cool. Yep, you should be presenting it. I will be back in 2 seconds.
No worries. Alright, so basically the easiest way to convert between different numbers of systems is using the calculator that comes on the computer. So what you can do is on the computers in the labs, on your own computers if you've got Windows, just the normal calculator app. So you open that up. You see on the side, or if you go to the menu, there'll be a few different options you have here. So what you can do, I'll just make that a bit bigger, you can just click on Programmer, and then you can actually get this to convert between different number bases for you. So also a number base that we do have is octal. So you would have seen this in the quiz, some of you. This is a base 8 number system. So binary is base 2, octal is base 8, decimal is base 10, and hexadecimal is base 16. And all you have to do to convert them is you just type in the number, so the number in decimal, let's say 56. It'll tell you straight away what it is in hexadecimal and what it is in binary too. So this was what shows on Windows 10. If you have an older version of Windows, the layout's a little bit different, but it's essentially the same principle. Same thing as well, if you want to start in hexadecimal, let's just clear that. So let's just say you wanted to work out what, let's say 56 in hexadecimal, and it turns out that's the same as 86 in decimal, or the same as this in binary. So this is a really cool way. You can check your results. So on some of those quizzes, you can do the conversions nice and easily. If you wanted to do these by hand, it's a little bit more involved. One of the ways that you can do it, and I'll go through this quickly because it's not as important because you do have a nice, easy way to be able to do these things. But let's just say we want to convert 56 into hexadecimal. So what we do is we start with 56. We divide this by 16. 16 because this is base 16. And we get 3.5 as our answer. Alright, so what we do is we leave the 3 here. So we need to actually work out 56 divided by 16 is 3 with a remainder of 8. So 16 times 3 is really bad at calculations. 48 with a remainder of 8. Then what we do next is we just follow the process through. So we will, where is it? over here. Cool. So we leave the 8 with a remainder bit, and then we take the 3. 3 divided by 16 is 0 with a remainder of 3. So what we do is with these remainders, we just read upwards, and we get 38 as our answer in hex. This extends to the different number systems, but as I was saying before, you've got the calculator here. You can convert between all 4 different number systems really easily. You can also start in binary, type in like a big binary and get the conversions happening.
The other thing is that most scientific calculators actually have that feature as well of conversion. So just have a look at your manual or look online how to get between them. Because if in the exam you need to convert, you should have your calculator and you should be able to do it.
Cool. So did anyone have any questions on that at all? And there are some other tricks as well you can work out with hexadecimal and binary, but it's probably not worth going into too much detail into that. But definitely feel free to ask questions in the labs, or even if you're on the chat, if you are interested, we'll go through it a bit later, but there's no point if no one's interested. So cool.
Them just see it.
Yeah.
All right. Let me get my list up. All right. I might do the while and do while loop.
Infinite windows. Yep, that's cool.
And then I'll get you to do overflow and underflow.
Sure.
Sound good? So
yep, sounds good.
Let's do the screen. Okay, so something you'll see this week in your labs is looping. So looping is helpful when we want to do something over and over and over again. What are you? So the first loop we're going to look at is the, oops, I can't spell. The while loop and the do while loop. The while loop is one that basically works by while a condition is true, it will continue. The do while loop, on the other hand, it will do it once and then will continue doing it while it's true. So the difference between these loops is only one thing. This one, oops, why is that color not dark? This one will do once, always. Where this one will only do while the condition is true. So that's the difference between do and while loop. So let's have a look at them. So a while loop has the syntax of while. Similar to your if statements, it has some brackets where a condition will go, and then it will have these squiggly brackets and everything inside them. Whoops, I want green. Everything inside them will loop while this condition is true. The other loop, do while loop, has the syntax do then the squiggly braces, then a while, then the brackets. Now this is really important. There is a semicolon here, because this is one big statement. Do not forget the semicolons here. And same thing, this will loop, and this is the condition. So let's look at an example. I wonder if I can go up a bit. Alright, so let me get another pen. So if we have int a equals 7 for both of these, and then we have while a is less than 9, and then in here we have a plus equals 1. There's also the increment operator we could have used there, but I don't know if you've been introduced to that yet. And the condition will go here. So let's have a look at what happens differently between these. So this one, we're on this line. A is of value 7. On this line, A is of value 7. We get to this loop here on this one, and we check, is A less than 9? Well, it's 7, so it is. So that's all good. Then we get here, and now A equals 8. There's nothing checked here for this one. We get here, and A is added. Then we check it. And so is 8 less than 9? Yes, it is. So this one, as I said, it will loop, goes back up here, and checks, is 8 less than 9? Yes, it is. So it will go in here and do this operation. So A is now 9. And we'll go back to this one. So for this one, we're here right now. This one, we go A plus 1, and A equals 9. Then it will check here and go, okay, A isn't less than 9 because 9 is not less than 9, and it will exit and do the code below it. This one goes back up, checks, no, it isn't, so it will go back down and continue. You can see that both of them did something very similar. So why would you want to use a do while over a while? So let's look at a different case where we don't have the same, where we want to do something once. So if we're going to so let's say int a equals 0, int a equals 0. Now let's say we've got, well, a is not equal to -1. A not equal to -1. In this case, if we do something up here and we ask the user to enter something, and we say, let's say %d, and we put, let me move this up a bit. Let's actually move this down a bit. Where's the... one to do. Okay, let's move this down a bit. And let's move. Actually, let's just delete those. All right. So I'm back here. All right, so we've got. Well, A is not equal to.
Didn't sound good.
Just wait for feedback. Sorry about that. Okay. Oh, now I've really done it. All right. Sorry about
Broken
that. Yeah, I've broken everything. Now we've got int A, and then we ask the user something, say printf, enter a number. And this is for both of them. And then we have scanf, %d, and %a. Now, and then we do a minus equals 1. So the big difference here between these two loops is, let's say the user, so we create A for both of these, and we ask the user to enter a number. And let's say the user enters -1. Okay? In this case, we get here and it does the condition. While A is not equal to -1, well, A is -1, so it will exit. With this case, it does this do first. Then it will do this. So A minus equals 1, so it'll subtract 1. So we get -2. And then it will check, okay, A is not equal to -1. So it will go back up and do it again. And this will actually continue until it overflows. So it will keep going down. So the difference here is if you do something beforehand, and this one may not execute, where this one here will always execute once. Now, what's a really good use for this do while loop is if you're going to ask the user a question, so if I was going to ask the user a question, printf, enter a valid number, and then I scan for their valid number. A. Then I can check while A is valid. So let's say A is greater than 0 because I don't want negative numbers. So what this means is that it will do this, then it will get the value, and if it's wrong, it will ask again, and it'll ask again, and it'll ask again. So this is where do while comes in really handy. While comes in handy if you've changed something beforehand and you don't want it to loop if it's not a valid number. So just remember, this one always executes once. Is there anything you want to add about do while?
No, I think it's just about it. Those are the main differences, really.
Was there a while loop in the assignment? I can't remember.
Neither.
I don't know if there's a while loop, but there is a for loop. Let me double check. Where's my answer? I don't think I put a while loop. I think while loop was if you wanted to. Oh, yes, there was a while loop, I'm pretty sure. If you wanted to check assignments, no, labs, format. Where do I put all my answers? Assignment 1. Yes, it is actually applicable to the assignment. So in the assignment, we said if they enter an invalid type, then you should keep asking the user. I think that was an extra thing. Let me get up the assignment sheet. Where is it? Assignment 1. My computer is so slow at the moment. Alright, so... Yes, so it is actually applicable. So if the user does not enter a valid value, i.e. 1 or 2, the program should print the following: invalid input, please try again, and then do it again. So you can see here in the assignment that it asks it once, then if it's wrong, it'll loop and continue looping. Okay? So this is going to be either a do-while loop or a while loop. The other part, there's a hint that it's a for loop, and we'll cover the for loop in the next part after Josh goes through overflow and underflow. But yes, this is all applicable to the assignment. All right, is there anything you want to add to do-while loops? While loops?
No, I think you've hit it all there for those ones. So.
All right, I'm going to chuck it back to you to cover overflow and underflow.
Awesome. All right, so this is another topic that, again, sometimes in your code you'll get some things that happen one way and you don't expect them to. So what we're talking about with overflow and underflow is if we have maybe an integer, and let's just say we have a 16-bit integer, just to make it easy. So this goes into what Matt was talking about before. So 16 bits means we have those 16 light switches that are either on or off. Now, what actually happens is we've only got 16 of these light switches. So what this means is if all of the light switches are turned on, we get a really big number if we make this an integer. And let me bring up the calculator and let's see what this number is. So we're going to go programmer, binary, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Cool. So we can see that this number here, when we have 16 bits and all of them are turned on, we have a number that comes out to be 6, 5, 5, 3, 5. All right, so, and again, like what we were talking about before, this is how we can write it in decimal. This is how we write it in binary. So what we see here is that our variables actually have a limit in how much they can store. So we can see here that if we have a 16-bit integer and we turn all of those switches on, we get a number 65535. Now, what do you think will happen if we try and add 1 to this number? Now, if we did this, we expect it just to be 65536. But going back to how it looks like with all our bits, we can see that all of the bits are turned on. So if we try to add 1, they're all 1. So what actually happens? And this is where we get into a thing that we call overflow. What happens is we try and add 1 to this number. When we add 1 in binary, this turns into a 0. We have a 1 here. 1 plus 1 in binary becomes 0, 1. And we see we can follow this pattern all the way down the line. And we can see on the calculator what actually happens is if I add 1, this is how the number looks. So all of those 16 bits at the start have turned to 0 now, and there's a 1 at the 17th bit. Now just remember, this was a 16-bit integer. So what's actually happened is when we store this, we don't do anything with that 1. That 1 just goes away because we can only have enough room. We only have enough room for 16 of these light switches. So with that 17th one, we just kind of ignore it. So what's actually happened is we thought that when we added 1 to 65535, that'll give us 65536. But actually, if we're using a 16-bit integer, what we find is that when we have 65535, when we add 1 to it, we actually get 0. So again, this is something that can trick people up if they haven't seen this before. Because you'll be trying to add some numbers, the numbers will get really big. So maybe if you're doing some sort of maths program, like maybe a calculator, if you try and add 2 numbers and it gives you an answer that's bigger than this number here, and you're storing it in a 16-bit integer, you'll actually go back down to 0 and start again. And again, this changes if we had a 32-bit integer. I think that's 12, 16. Yeah. So again, we'd be able to count up to this number here, but as soon as we added 1 to this number, we end up going all the way back to 0, and we forget this 1 at the start, and that's what we call overflow. And is my voice coming through okay at the moment?
It's a little bit choppy.
Bit choppy? Fine.
It's better now.
Better now. All right, cool.
Yeah.
Awesome. I was just being a robot. So this is something we do really, really, really need to be careful to. Depending on how much we can store in our variable, if we try and store too much, then we end up going back to the start and counting up again. So if I added 1 to this, we just get 1. If I add another 1, we get 2, and so on. And then when I got to 65535 again, I add 1, and I get back to 0. Do you want to add anything else to that?
The only other thing is underflow.
Underflow, cool. So, and I'll see if I have a question that actually...
It's in the week before, I think.
It's in the week before, cool. Week 3 quiz?
Week 2.
Week 2, oh, alright.
I think.
Sorry, just a second, guys. Just trying to see if we have a question here when I can actually apply it to an example. What's this one?
You can give the answers to these questions as well.
These are the week 4 questions. No, week 3.
Week 2.
Week 4 quiz. I'm so
it's week
confused.
4. I don't know which one overflow was under. Is it week 4?
Yeah, this is week 4, so maybe I want to give them away. Anyway, so yeah, so we talked about overflow when we go too much. Underflow is something a bit different. Is we're talking about signed and unsigned yet, or?
Well, you can mention that. You can introduce that if you want. Just quickly.
Yeah. All right. So underflow is something else that we have when we're kind of going. If we have a, what's the best way to explain it? I'll talk about signed and unsigned first.
Yeah, and then show an example with unsigned.
Yeah.
Unsigned. Yeah.
So something else that we've seen so far is you might have seen something where we have a signed int and an signed int. So I think there was a quiz maybe in the past where we've seen one of these or both of these used before. Now, what this is actually talking about is integers again. Let's just pretend that they can hold 16 bits. So they have a minimum and a maximum value. Now, when we talk about an unsigned int, this means that they only take values from 0 to that 65535 for a 16-bit integer. And the reason, again, is because we've got all those light switches and they're all turned on. So our number can't get any bigger than this, and it can't get any smaller than this, because that would mean they're all zeros. Now, we have this other thing where we have a signed int. So what a signed int is, and how it's different to an unsigned int, is signed ints can store negative numbers as well. So what we've seen with how we represent all our ones and zeros, when they're all in the on position, that means we've got the biggest number possible that we can have. But it doesn't actually let us do any negative numbers like this. Now what a signed integer does is, again, we have those 16 bits. But what actually happens is when C interprets how we're storing our number, it looks for the very first bit from the left-hand side, so the most significant bit. And this actually tells C if it's a positive or a negative number. So what this means is, I think 1 is negative and 0 is positive. Is that right?
What?
1 is negative and 0 is positive?
Yep.
Yeah. So if C sees a 1 here, this means that this one counts as a negative number. If it sees a 0, then it counts as a positive. And the best way to go about that without getting too confusing is we saw before that this guy here, he was worth 1. This guy here was worth 2. This guy here was worth 4. 8, 16, 32, 64, 128, 256, and so on. When we get to this guy, he's like 3, 2, something, something, something. Now, if he's a 1 and this is a signed integer, this actually counts as negative 3, 2, something, something, something.
Minus 1.
And then we, hey?
Minus 1.
Minus 1?
Yeah.
Oh yeah, yeah. So if this is a 1 here, this means that whatever this number is here, it's like 32,000. It counts as negative, and then we're adding up all of these numbers to get our final answer. And this is how we're different from...
Not quite right. You actually have to use 2's complement.
Yeah, 2's complement. This is how it's interpreted by C, though, when it just sees a signed integer, though, right?
Yeah. No, it's stored in 2's complement form.
It's stored in 2's complement. Okay. Is it worth going through that too? We're going to go through that as well.
Nah, don't bother.
No. All right. Essentially, long story short, though, if we do use this signed guy, we're using one of these bits to tell if it's a positive or a negative number. So we've only got 15 of these guys left. So that means that the range of our number that we can store now is smaller than this range here. So it's like -3 to... Do you know what it is off the top of your head? -32768 to 32767. So the range has actually changed because we can now store some negative numbers. So again, this is something to watch out for too. If you're trying to store your answer in an unsigned integer, and you've got 0 over here as the smallest value we can take, and 65535 is its biggest value, and maybe you try and work out what 5 minus 10 is. If you store that in a signed integer, that'll tell you it's -5. No worries at all. If you try and store it in an unsigned integer, though, we're going outside of our range again. So we're going to see some weird results that we're not expecting. So that's something else you need to watch out for as well. Make sure if your number's not going to have any positive or negative, it's only going to have positive values, you can get away with using unsigned. By default, though, you use a signed integer. So when you just say int just by itself, C actually makes that a signed int in the background. So you don't have to worry too much about that. And as for more into the underflow,
Show an example with unsigned.
With unsigned, so I don't know. Tell me an equation.
For unsigned, oh, I don't know. 5 minus 50.
5 minus 50. All right. So again, for our 5, if we represent that in our binary, we've got 1, 0, 1, and 50 is 32, 16, 48, 8, 4, something like that.
That's correct.
Of course it is. So when we try and subtract these two, we can see that if I just set this up, the 1, 0, 0, 1, 0. Cool. If we try and set this up and we try and do the subtraction, you can straight away see that we don't have enough ones up here to be able to actually do the subtraction. So we're gonna, when we do the subtraction, actually loop around again, and our answer is going to be up towards the top of our values here. Kind of the opposite to what we saw when we did our overflow. This is what's happening when we're going the other way. We're going too low. We can't actually store this negative number, so we're going to go all the way back up to the top. And if you can imagine, this is 16 bits long, so we're going to get a pretty big number at the end of it. Do you want to add more to that? I feel that I haven't explained that very well.
That's all right. As long as you understand the concept that you've got a limited set of numbers, it's a limited range in your types. So we saw with the floats versus ints, the limitation was that one can hold things after a decimal point, the other one can't. The same with int, it can only hold up to a certain value and down to a certain value. And then if we chuck on the unsigned or signed type to them, the unsigned type can only hold positive numbers, where the signed type can hold both signed and unsigned. But it also changes the values that it can hold. So if you choose to use a short, you'll limit the amount of numbers you can hold also. If you choose to use a long, then you can hold more numbers. So it's just really important if you know, for example, that you're going to calculate the height of the biggest tower, and you're using a number in meters, and you know that it's going to be greater than 65,000, then you know that int is not going to be enough in this case. So you're going to have to use a larger type, or you're going to have to divide your number down. All right? Yes. All right.
Cool. So that's just something definitely to watch out for. If you're trying to add two numbers together and you get a number that's smaller than what you started with, it's probably because of this reason that that's happened.
All right. I'm back on. Why is it showing not my screen? I should be presenting. It's showing my screen on YouTube. Hurry up, YouTube.
You'd be delayed, wouldn't you?
Yeah, but no, it's not the delay. It's not showing my screen.
Hmm.
Come on. Stop being slow, YouTube. Come on. Now it's showing your screen again. Now it's showing. Why is it not showing my screen? That is weird.
Are you sharing it properly?
What?
Are you sharing your screen properly?
Yeah, I'll turn it off.
There's you.
There is me.
Hello.
Hello. Let me turn it back on.
Hey.
Hey.
It's
There we go. All right. Sorry about that. You can blame Josh. It was all his
wasn't
fault.
me.
All
Sorry,
right.
guys.
So the other loop, and one that's really important for the assignment, is the for loop. So this one is different in that it has multiple things you can set to make it operate. So the syntax for a for loop, give me a black, is for like this. It's got 3 values you must put in here. This one here, this one here, and this one here. So this one here is this one's the initial value, this one's the comparison, and this one is the update, the last one. You can find the more formal names in the lectures if you want to use the formal names. I don't really care. All right. And how these fit in is if we look at it as a block diagram. So we come into the for loop. And this here is code. Who are you killing, Josh?
Sorry. Everybody.
So what happens is this initial part will happen first, then the comparison, some kind of comparison, then the code, then some kind of update. Now, the comparison will only go to the code when it's true. I don't write Y. When it's true, and when it's false, it will go down here. Okay? So false, else it will go down here, true. So let's look at a proper example. And one that will be very helpful for your assignment and this week's lab. Okay. So let's say we've got... Actually, let's make it even simpler. So generally when you're iterating, we use the variable name I for iteration for one for loop. Now, when we say keep the names meaningful, I itself is actually meaningful because it's commonly used, and when you see I, you know that there's going to be a for loop coming up. When you see J, usually that means there's a for loop within a for loop, and when you see K, it means that there's a for loop within a for loop within a for loop. So don't be afraid to use I. It is commonly used unless you want to give it a specific name for some purpose, but I is acceptable. You won't lose marks for using I. So we declare this variable I, and then we write for I equals 0, which is our initial condition. I is less than 2. I plus plus. And we'll print something out. Printf hi. with an exclamation slash n. Okay, so we've got this code here. And let's draw up a block diagram of that. So the first thing that happens, we come in and we've declared int I. We then do the initial part of the for loop. So I equals 0. Then we check, is I less than 2? If it's not, then it's false, and we go over here. Else if it's true, oops, I keep hitting that. Else if it's true, we do this. So if it's true, we do the printf. I'll just realign the screen. There's nothing in the chat. And then after the printf, we come back up because we hit this. We go back up here, and we do this increment, then compare. So we have I plus plus. Now I plus plus is the exact same thing as I equals I plus 1. And you can actually write I equals I plus 1, I equals I plus 1 if you prefer, if you're not comfortable with that at the moment. Okay, so this is what's happening. So we declare I, we're here. We then get here. So let's look at I. We'll store I here. We get here. We now get to this for loop, and what happens first is I gets set to 0. So I is 0. Then we compare, is I less than 2? Is 0 less than 2? Yep. So we go into the code, and we print I in the new line. We then go back up, and we add 1 to I. We do this part, as can be seen here. So now I equals 1. Then we compare it. So is 1 less than 2? Yes. So we go into the code, and we print out I again. Then we go back up, and we add 1 to I. So now we've got 2. Now that we've got 2, we do a comparison. Is 2 less than 2? No, it's false. So it finishes and does whatever other code. So we end up with 2 highs. Now, let's change this a little bit and go, well, I is less than, let's say 8. Oh, it's probably a bit big. Oh, that's okay. Well, I is less than 8. And I equals I plus 3. Okay, so we've changed this to an 8. And we've changed this to I plus 3. Okay, so this time we create our, why does it do that? We create our I variable. So we've got I here. And this equals nothing at the moment because we're here. We then go into our for loop. We set I to 0. If we change that 0 there, we can change it to another value. I've lost my pointer. There it is. Then we check, is I less than 8? Yes, it is, because it's 0. So we print out I. Then we go up here and we add 3. We add 3. So now I is equal to 3. We then print high again. Oh, we compare it, sorry. Is 3 less than 8? Yes. So we print again. We go back up. We add another 3. So now I is equal to 6. Is 6 less than 8? Yes. So now we print high again. We add another 3. And we get 9. Is 9 less than 8? No. So we go down here. Okay, so we can do looping based on adding a certain number to a certain condition. So another thing before I go to the assignment and show you how this relates. Now, be very careful when using values here. A lot of people accidentally do things like this. I equals I plus I, or they'll put another variable here that changes. So if I put I here, or if I had, say, int, another thing that may happen. So be careful here that you are using the right variables. One example I did see today from an email was, say you've got int A and you give it a value. So let's say 30. If you then create a for loop and put A plus equals A, whatever value it was here just got overwritten by 0. So if you're setting it as a value, do not use that same variable here, because what happens first is it gets written over by this first condition. You can leave that blank if that's your intention, but whatever happens here will overwrite whatever it was before. So just be careful. It's good practice just to use an iteration variable such as I to keep track, and don't use variables that have values such as this one. Now, let's go back to the assignment. Let me just refresh that. So, in the assignment, the program starts, the values start at 0. So similarly here, we saw a loop that starts at 0 and increments by the step value. We saw each time it increments by something while the value is less than 360. We can see that this continues while it's less than 8. Now, even though it says while there, you could do this with a while loop, but because you've got the other conditions, the 0 and the incrementing, a for loop may be more appropriate. However, anything you do in a while loop, you can actually do in a for loop, and anything in a for loop, you can do in a while loop. You just need to choose them when they're most appropriate. So you should be able to do that given the for loop. And the same thing here, the value starts from 0, then increments by a step value, while the value is less than 2 pi. So persons in the chats, does that help with knowing what to do for the rest of the assignment? In the assignment, is there a way of avoiding using pi? No, not really, because pi Well, 2 pi is the definition of the circumference of a circle. So, no, you can't really. Good work, Antonio. Good work. He's just written that he has done the assignment. But no, there's not really a way to get around pi in the assignment. You can avoid it in a couple of places, but you still need to use it. Okay, that's not a bad idea. Okay, so someone just asked about commenting as well. Let me just see what I've got on my list.
Yep.
Because I think we've covered well. The only thing we have to cover is bitwise and some commenting. I think that's it. Was there anything you wanted to
sounds good.
Anything special you wanted to add?
No, I think what we've been through and what we're about to go through is all should cover most of the things.
Okay.
Especially most of the questions we've had this week.
All right.
Go ahead.
What was I going to do? I'm going to delete all this. Hopefully that makes sense with the for loop. It's pretty important, and it's going to be important for this lab and this assignment. Okay, commenting. Let me just see if I've got something that you've already done. Can't use that one. Let me get. Okay, so let me get this one up. Okay, so this one hasn't gotten any comments whatsoever. So there's 2 kinds of comments we're looking for this semester. Firstly is just professional comments in general. So comments that relate to the domains that normal programmers would not be able to understand while just looking at the code for the first time. And also comments to show that you actually understand what you're writing. So if you just copied what was written in the lab sheet or copied off your friend, you haven't really learnt anything. So we want to see that you've learnt something. So what we want to see at the top is a multi-line comment that says something about the problem. So something along the lines of, this program is a calculator for finding the equivalent resistance of 2 resistors. Sorry about my spelling. In series or parallel. And then you'd list the calculations or whatever background information. I won't write everything there. Then what we also want to see is anything special that you're using in the code or anything new. So give a short description of in this code, we use both getCar and scanf to get values from the user. We use if statements to see which type of input the user wants. So short description of how the code runs. It doesn't have to be very long. And then comments alongside. Now for this, anything that's new, we want to see that you comment. So scanf is new for this week. So explain what scanf is. So scanf scans the input buffer in the console for integers and stores them in stores the integer in variable resistor1. Okay, so anything new, give a short description of what it is. Now, you should also explain bits like this. So for a coder, if you've already done printf, you don't need to explain what the printf is, but you might write a short comment like asks the user for the value of resistor 1. So just something short. You don't need to explain printf though, because we know what it is. However, here, we don't know what you're doing here. So you could write something like calculates the equivalent resistance value for parallel circuit, something like that. And float is used, and the float typecast is used to get a floating point result from the division. So it explains why you've done this calculation and also why you had to put this typecast here. So it shows that you understood this, but you can also write comments that relate to what a professional would be looking for. So you should try and write as many comments as possible to show your understanding, but also to show that you can explain your code to someone else. You don't need to put a huge amount of comments about things you've already learnt, so you don't need to explain int or float or character. Last week we did scanf, so it would have been good to see that, but this week you don't need to explain that. You could just write gets the resistor value as an int from the user or something along them lines. All we're looking for is to show that you understand what you're writing. Does that make sense? Person in the comments? Cool. Anything you want to add about comments?
No, I think you've hit it. As long as they're to the point, there's no point making them sort of like an essay that just doesn't really hit the point. Just it's the main thing for comments.
If you feel like you need to write more, put it up the top. So the detail can go up the top. The comments in the actual code should be fairly short. Anything of detail, if you want to explain something in detail, put it up the top. Cool. So that's comments. And last but not least is bit. Let me get up my we only do half of them. Might just take. Do you want to just take a 5-minute break, and then I'll do that. Or you can. Are you gonna stay on?
Yeah, I'm gonna. Yeah. Always happy. Do you want me to do some stuff?
It's up to you. We can take a break as well.
Oh, I don't mind.
Been on for 2 hours. I'm wondering.
In the interim, I can do some MSP stuff.
Well, I was going to say, if you want to, there's more quiz questions there, or just take a 5-minute break.
Did you want me to go through bit bashing at all, or are you gonna?
I'll do that. I'll do that.
You do it. All right.
Yep.
Okay. Well, in the meantime, does anyone have any questions I can answer while we wait for Matt? Otherwise, we can all take a break. Need some elevator music. All right, so we have a question. So for the for loop, is there any other way of writing it? Short answer is no. So basically, the for loop always needs to look like this. Colons inside there. The best practice is always to include stuff in here. So as we were saying, this is the update condition. As it. You can leave some of these blank. Normally, you don't want to do that though. If you wanted to leave some of these blank, then potentially you could use a different kind of loop to solve the problem that you're looking for. So always, for best practice, always try and keep these populated. And that's that's how you write the for loops. Again, if you're finding that you don't want to always do all of these 3 things here, you're probably better off using a different loop because there's probably better ways to do it. Does that answer your question? Awesome. Cool. Are there any other questions? Otherwise, I'll bring back the elevator music.
I like that.
It's pretty good.
You're a smartass. Did you time that like perfectly?
It's on loop.
Okay. Well, are you playing Mario? Did you
give it a like?
Did you answer this question? The for loop?
I did, yeah, the for loop one. Yeah.
Yep. Cool. All right. So I'm going to steal the screen.
It's all right. Can I have it for a little bit longer?
Why? What do you want?
I'm just gonna wait. Oh, never mind. Okay. You can you can put it back on my screen if you want, and then you can take it away.
I think I did.
Okay, I don't think I had it on the screen at the time, but that's all right. Doesn't matter.
All right, cool. Okay, so before I do that, let me get up LMS because this. Okay, so this is this week's lab. If you haven't seen it already. And up the top here, it actually gives you these 4 bit operations. Now, when I say bit operations, this means things that happen to bits. So when we saw before, where's my pen? Make the screen a little bigger. We had so we had what's going on? Something's screwed up. Come on. That's some. I don't think we want calligraphy. What is it doing? Sorry. It's. I have to reopen. That. That's better. Cute. All right. So we saw earlier that numbers are stored as bits. 1, 2, 3, 4, 5, 6, 7, 8. Yep, cool. Okay. So numbers are stored as bits, and they'll either be a 1 or a 0. So for example, 1, 0, 1, 1, 0, 1, 1, 1. Now, we can actually manipulate this so that we can take control and toggle each one of these bits on or off individually using a single statement in your code. Now, one thing to remember, this is actually bit 0. This is bit 1, 2, 3, 4, 5, 6, 7. It goes backwards and it starts at 0. Okay? So if you want to access bit 0, it's this one. If you want to access bit 5, it's this one. It's not the other way around. All right. So the first thing we can do is this. We can do, okay, so let's say we've got a variable called A, and we give it the binary number, give it an int, 111 0 1 1 0 1. Okay? And what I want to do, I want to turn this 0 into a 1. And how I do this is by writing A or equals 1 shifted by 1. Now, let's unpack that a little bit. So if I run this code now, my binary number will become 1, 1, 1, 0, 1, 1, 1, 1. Okay. Now, this here is really important to remember, and this is setting a bit. Now, how this works is, oops, we saw earlier that a times equals 4 is the same as writing a equals a times 4. Or if we write b plus equals 7, it's the exact same thing as writing b equals b plus 7. Yep. So this here can't write everything out. This here is exactly the same. I'm gonna put another color. Let's go pink. A equals a or 1 shifted one place. Now, that's a 1. This line here is different than a conditional or. So we saw earlier we had these two lines. Now, this is used for, someone's asking, yes, they do get recorded, and I'll try and add annotations, but it's only when I have time. But yes, they are recorded. However, it's better if you can come in because it helps us continue running them. All right, so this symbol here is a bitwise OR, where this one is a conditional OR. So this is a condition. So if we had an if statement, we compare two things, we just put the OR in between. This one's used for bits. This one's used for conditions. They're two separate things, but they both mean OR. All right, so let's have a look at how this works. So the A will equal 1, 1, 1, 0, 1, 1, 0, 1. Then 1 shifted 1 place. So let's have a look at these. Let's open these brackets up. I can rewrite 1 as 0, 0, 0, 0, 0, 0, 0, 1. And what a shift operator does is everything this amount of places. So let's actually show you another example. So if I had 1, 1, 1, 0, 1, 1, 1, 0, and I shifted it 2 places, it would become 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, because it's moved 2 places to the left. If I do the opposite and shift it 2 places to the right, then it would become this, because everything has been shifted and these 2 digits have been shifted out. So that's all the shift operator is doing. So we've got, I'm running out of room. I'm going to move all this up. So we've got this, and I've got the wrong tool. It's gone again. What's going on? Sorry, I don't know what's going on here. Something's stuffed up. Sorry, I don't know what's going on with this. I'll do this. Come on. Let's go. No, nothing wants to work, Josh. I don't know why.
Okay.
Yeah.
You broke it.
I think I broke it. What I'm going to do is just close this. And actually, what I'll do this. Sorry, guys.
Would you like some elevator music in the meantime?
No.
Okay.
Everything starts breaking now. Is the pen working? Yes, it's working again. I don't know what happened there. Okay, so let's go back to the example. Sorry about that. Is that 8? Yep. So we had 1, 1, 1, 0, 1, 1, 0, 1. And we had int a equals 0b 1, 1, 1, 0, 1, 1, 0, 1. Then we were doing setting a bit, which was this. So this one here is choosing which bit. So in this case, we want to set this bit because it's number 1. So let's unpack it, and we get a equals a, or 1 shifted 1 place, which equals 1, 1, 1, 0, 1, 1, 0, 1, binary OR. Then we have 0, 0, 0, 0, 0, 0, 0, 0, 1, shifted 1 place. So then we get 1, 1, 1, 0, 1, 1, 0, 1, and this all goes 1 place to the left. So we get 0, 0, 0, 0, 0, 0, 1, 0, because it's moved 1 place this way. Okay. Then we do a binary OR. And this is different than a conditional OR. Remember, this is the conditional OR, as it's comparing each one of the binary bits. So 1 and a 0 is a 1 because there is 1. So a 1 and a 1 is a 1, a 1 and a 0 is a 1, a 1, a 0, or a 1 is a 1, and a 0 and a 0 is a 0. And this is OR. And it's actually the same for conditional ORs as well, except for it's not looking at bits. So what it's doing is, because we've got 1s here, they stay the same. We've got 1s here. Now, when these two are compared, this one and this one, it's a 1 and a 0, so the OR is true, and so it gets set to a 1. And what we've done, we've set that 1. So this is setting a bit. And we've successfully set a bit. So another example. Would be if we want, sorry, I should have deleted that as well. If I wanted to set this bit to a 1, then I look here, and that's bit number 4. So I change this to a 4. And if I ran this code, then my binary number would be 111111101. So I didn't do that one that time. That was last time. Okay. So that's setting a bit. And basically you just put the bit number here. And we'll see why this is handy shortly. Where did I put that? There we go. So the next one we look at is clearing a bit. So we've set a bit. We've done that. Now let's look at clearing a bit. So let's add a line to our code. And I'm trying to write with the eraser.
You need a different colored eraser.
A and equals not, and this is a binary not, 1 dash dash, and then the bit we want to clear. So let's say I want to clear. So we want to set this bit, and we want to clear this bit. So this bit is bit 6. Remember, it starts from the bottom and goes up. So we are clearing bit 6. Okay. Now let's unpack this and let's see what it looks like. So we've got A equals A binary and. Then we've got a binary not. So just comparing between conditionals. So this is conditionals. And these are binary. So there's a binary equivalent for each of these. And then we've got 1 dash dash a slash slash 6. So A is equal to 0. Oh, sorry, no, it's not. It's equal to 1 1 1 0 1 1. Well, this one's actually set now because we set it up here. So we can actually put that as a 1 as well. 1 1 1 1 1 0 1, because remember we set it here. And not. Then we've got 0 0 0 0 0 0 0 0 1 shifted 6 places. So let's do the shift first. So move this across 6 places. So 1, 2, 3, 4, 5, 6. So we end up with this. We've got the not and the and the 1 1 1 1 1 0 1 here. When we put the not here, it's a binary not. So it basically turns all the zeros to ones and all the ones to zeros. So we've got 1, 0, 1, 1, 1, 1, 1, 1. And that's correct. We've got the and 1, 1, 1, 1, 1, 1, 0, 1. So when we had the or, a 1 and a 1 became a 1, a 1 and a 0 became a 1, a 0 and a 1 became a 1, and a 0 and a 0 equals 0. Where an and is
1 and a 1 equals a 1. 1 and a 0 is a 0. 0 and a 1 is a 0. And a 0 and a 0 is a 0. Okay. So let's have a look what happens here. A 1 and a 1 become a 1. And then the one we're setting is a 1 and a 0. So this will become a 0. And then 1, 1, 1, 1, 0, 1. The 0 still stays because it's a 0 and a 1. And so we've successfully cleared that bit. Beautiful. So now we're able to clear and set bits. Actually, what I'll do, I'll grab this. I lost my mouse. There it is. Delete all that. Delete all that. I wanted to keep that. Just clean all this up. Clean all this up. Move that across. Cute. Okay, so now we've got our setting, we've got our clearing. So we've set this bit and we've cleared this bit. Now another operation we might want to do is toggle a bit. So when I say toggle, I mean if it's a 1, turn it to a 0, and if it's a 0, turn it to a 1. So let's say I want to toggle. Let's say we'll toggle this one. So this one's set. This one's clear. And with your list, you want to toggle. So to toggle, we use a new operator, which is called an exclusive OR. And we want to toggle bit 5. So I kept deleting this. So OR is that, and is that, and XOR is this. And XOR is different because a 1 and a 1 is 0. A 1 and a 0 is 1. A 0 or 1 is 1. And a 0 and a 0 is 0. Where the OR was 1, 1 is a 1. 1, 0 is a 1. 0, 1 is a 1. And 0, 0 is a 0. And it's just when 1 and 1, then it's a 1. Okay, so let's unpack this, and we get A equals A XOR 1 shifted 5 places. So once again, 1, 1, we've cleared this bit here, and we've set that bit here, so this one's actually a 0 now. We've got a 1, 1, 1, 1, 0, 1, XOR'd with 1 shifted 5 places. So let's look at 0, 0, 0, 0, 0, 0, 0, 1, shifted 5 places to the left, which gives us 0, 0, 1, 0, 0, 0, 0. XOR 1, 0, 1, 1, 1, 1, 0, 1. So a 1 and a 0 gives a 1. 0 and a 0 gives a 0. We're just going according to this. We get to bit 5. And these are now 1 and a 1. And so we get a 0. So it's toggled it. It's changed it from what it was before. So this bit's been toggled. And that's how you toggle a bit. And I should put a semicolon there. Now, this is all good, but why would we want to use it? And this is where the last one comes in. And this one can be used as a condition if you want. I wonder if I can just do something. let's just make that a bit smaller. So let's delete this line. And let's get my red pen back. And this is toggle. Now, the last thing we want to do is check if a bit is set or cleared. So if it is 1 or 0. So to do that, we use A and 1 shifted to the bit we want. Now, this by itself is going to not be very useful as a line of code because it's not stored anywhere. So what we can use it for is for a condition. So we can say, we can say if A is set. And now if, let's say, bit 3 here is set, then we do something. So let's say A and 3. And basically this will work by going if A, so 1, 0, 0, 1, 1, 1, 0, 1. I'm using the version after this has happened. And 1 shifted 3 places to the left. So we've seen that already. So 0, 0, 0, 0, 1, 0, 0, 0. It's gone 3 places to the left. And now if we add these together, a 1 and a 0, it's going to be a 0. It's going to be a 0. A 0 and a 0 is a 0. 0 and 0 is 0. 1 and 0 is a 0. And we get to this one. And because they're both 1s, oops, I think I did too many 0s here. It will return a 1. The others are 0s, so these are 0s. So if we remember from earlier in the stream, we talked about if 1, if 0, or if any number. So this is true, and we'll go into the if statement. This is false, and this is true. So because this was set, whatever is the next, whatever's inside the if will happen. However, if this was a 0, let's say, then a 0 and a 1 would become a 0, and so this would be false. So why would we use bits? So bits are pretty much the smallest size that we can possibly get in terms of memory. So if we want to set flags, so for example, let's say you've got a variable, you've got a couple of variables. So you've got int user logged in. You've got another variable called int user user error. You've got another variable called user give me a variable, Josh.
User
happy.
registered. Yep. User happy. User alive.
User happy. Yeah, user alive. And user registered.
User hungry. User registered. User hungry.
Okay. And user hungry.
User thirsty.
Oh, that's enough. Okay. So each of these ints are 32 bits long. So we've got a lot of them here. All of these things are basically true or false. So user logged in is going to be 1 or it's going to be 0. So we don't really need all these 32 bits. So instead, we could just declare one int and then use bit 0 for this one, bit 1 for this one, bit 2 for this one, bit 3 for this one, bit 4 for this one, bit 5 for this one. And we significantly reduce the amount of memory. And then if I want to check if the user's logged in, then I can do a test, which was a and 1 slash, so I'll get rid of this int. So if I wanted to test if the user was alive, I would just do if a and 1 and the bit that refers to the user being alive. If they're alive, then things are good. If they're not alive, bad. Okay, so this way we can basically set flags for values that are true or false and push them right in just to store them in their smallest form. So this won't help with storing large numbers, but you can do this for single digits. And later when we do structs, you can do small numbers as well. Oops, that's not what I wanted. There is some other things that we will do with bits, but that will be next week. All right. Is anyone in the Hangout other than you?
Just us.
Just us. Beautiful. We've got a couple on YouTube. Was there anything else you wanted to cover?
No, I think that's about it.
Any questions before we go? Anything about what do you think of the Star Wars trailer?
Star Wars trailer?
Yeah.
Haven't seen it.
Oops. What are you doing?
Me.
Any questions? Any questions? Any questions? I think we need your elevator music, Josh.
I think so. Was that a good thing? Like, should we bring the elevator music back next week?
Possibly.
Possibly. Okay, hang on.
Stop breaking. It might be copyright, Josh.
It's all right. It's for educational purposes. It's fine.
Doesn't work like that.
No, I actually know the person that made it, so it's okay. Are you ready?
Okay. I really do I believe you? Let's put it up here.
pretty impressive. You're a good drawer.
Not really. I'm rushing. Bad English.
There's 6 watching, but there's a.
Yeah, no, that's the funny thing. I just leave it.
Maybe they've just forgotten about us.
Maybe they just left it open out of sympathy.
Yeah. They're probably stuck around for the elevator music.
They want more elevator music. I think that's the thing.
They do.
That's the most important.
We should play that at the start of every lab.
Every lab?
I think. Every lab. It can be like, thinking music.
Yeah.
So everyone will be conditioned to when they hear that music, they'll.
Where do we get help for our assignments if we need? Right here, right now. What help do you need for your assignment?
Elevator music is a nice touch. Sorry, carry on.
The first assignment, because it's worth 5%, we don't have many hours for help, so we can ask you to help right now. So if you've got questions about the assignment, ask them now or next weekend, but I prefer now because everyone leaves things to the last minute.
Will there be consultations?
Nope. Not for the first assignment.
Okay,
So
just in case people were.
They can come in and ask questions next weekend, and because we covered a lot this week, there won't be much to cover next week in the live stream. They can come in and ask their questions.
Yep. And they're allowed to ask us in the labs as well if they've got questions.
If there's time, the lab gets
Yes,
priority.
of course, yeah. Yeah, no, of course. I'm asking these questions in case people want to know the answers as well.
Yep. Yeah. So if you got questions, yeah. Salim, did you watch the part about for loops before? Were you here? Because I actually showed your problem. Okay, so I might go quickly back over that. I don't want to give away the answer though, so I might just do it with another example. What's my mouse? You watched it? You still couldn't get it? Okay. All right. So we've got. Oh no, wrong thing. We have a for loop, and we create a variable for iterating that's not affected by that we then set to 0. Let's say 6 I plus plus. Actually, let's do I plus equals Z. Okay, so we've got another variable here called Z that we want the user to enter. Let's say it's 2. So now when I do my for loop, it will go, I will become 0. So I is 0 and Z is 2. Then it'll check the condition. Okay, it's true. So it will do whatever's in here. So let's say this is a printf. Let's say it does a big Y. Then it'll print Y. Goes back up. It increments by 2 because Z is 2. And so I now equals 2. 2 is less than 6, so it'll print another Y. Then it goes back up. Z is still equal to 2, so it adds here another 2 to I, and now I equals 4. Is 4 less than 6? Yes, so it continues and prints another I. Then it comes back up. It adds another 2, so it becomes 6. Is 6 less than 6? No, so it ends. And we get Y, Y, Y. Does that explain your problem, Salim? Without giving too much of the answer away? We wait that 30 seconds. Yes. Yes, thank you. Cool. So without giving too much away of what you did, if you put Z here, let's say, if I put Z here, what will happen is Z is 2, and then it'll go 0. And so this will always be 0 and it'll never update. So this always needs to be a different variable, new variable, because it gets reset to 0. You can, however, do this. You can actually leave a for loop like this. You can actually leave a for loop with all of these blank if you wanted to. And you can actually set more than one thing in each one of these by using commas, but I don't want to confuse you too much at this stage. Any more questions? Any more questions, Josh? What is C?
Who do you think is
The best in the class?
the best in the class?
I can't say that because it's recorded.
Okay. Who do you think is the best demonstrator?
Can't say that either because I
Okay.
charge.
Who do you think is the best lecturer?
Can't say that because it's recorded.
Um,
You're not going to say anything that can be used against me, Josh.
someone in the chat.
Is that Josh is the best demonstrator? Or is that Josh, you're in trouble for saying that?
It's one of the two.
Dear. So if you haven't done the quiz yet, this is what next week's lab looks like, especially if you're on Monday. There is a little bit of maths, once again. This is probably the most mathy one. And then the week after, there's a lot less maths. So, yeah. You don't really need to know too much about the math because a lot of the code's given in this one. But what's really important about this one is this flow diagram. make sure you understand it. It also here in the green shows the for loop. As it says here, note the for loop is highlighted in green. When designing code or drawing out your code or trying to find bugs, it's a good idea to draw this out and then by the side write the values out, as well as doing debugging while you're going, printing out values. The second one is all about bit stuff. We create a little bit lock. Cool. And everything we've covered should allow you to do pretty much everything in this lab. So we've got a do while loop. Declaring some variables. Adding a for loop. Doing a summation. Calculations are here. And then this one. The first one's actually fairly easy this week. It looks intimidating because of the maths, but it's actually very easy. And the second one's a lot harder. That's expected. How's the project going?
Me?
Yeah, you.
What about it?
How's it going?
Which project?
The CS one.
Pretty good.
Sure.
We've, yeah. You'll see us at the end of the year, most likely. I'm kidding. Maybe. You never know.
Ah, you will.
Yeah, we'll see.
Cool.
How's your
Right,
project going?
Which one?
The CS one.
Actually, I've got a CS one, but I can't talk about that one.
Okay.
I think C is fixing C. Yeah. Anyways, any more questions? Before we go?
How's your other project going?
Let's just see if there's more questions, and then we can close, and then we can chat.
I don't want to chat. Yeah, I want to go to bed.
All right, we're cutting the screen. Unless you have questions.
It'd be funny if there were questions and they, like,
30
the delay didn't come through, and they're like, I'm going to ask a question, and they just hang up. No problem. Yeah, also as well, don't forget about leaving feedback each week. If there's stuff that you like that we're doing, stuff that you don't like, let us know.
I thought you were about to say, don't forget to like and subscribe.
That's true. It's your YouTube channel, so it'll be no good for me.
It's no good for me. I only put examples for people and stuff up. So, yeah. If you could, before you go, just something that Josh mentioned, really, really handy for us. Every week there's this anonymous feedback thing. There's also this special feedback that will open next week, this early subject feedback. Please put some stuff in there. We're trying to do a lot to make this subject a lot better. And we would really like the feedback of what you liked, what you didn't, what was good. So there's two places. This one's really important. I'll speak about that in the lab. There's also the ones for every week. If you can just chuck some feedback up every week, it makes a huge difference for us because it lets us do things like this more often. Okay? So chuck feedback everywhere it says feedback on LMS. because it helps us just